So hello everyone. This is lecture 15 for the solid state physics. So we are studying lattice vibrations, and in the last lecture I discussed some initial means what we're going to discuss is the monoatomic lattice, 1D vibrations, or the vibrations in 1D by the diatomic lattice. Means there are two type of lattice we will study. That is monoatomic, means single atoms will be there, and diatomic means the molecule with containing two atoms. So that's we're gonna study, and we started for the monoatomic in the last lecture, and I told you that how vibrations inside a solid cause to change the properties of solids, the thermal properties and the optical properties all vary according to the vibrations. Means they all depends on them, the phonons and all. So in the last lecture we were studying that we had a state of equilibrium where all the monoatomic states are there. Then we stretched the string, means not a string, the applied some force on the particles, so it act like a spring inside it, and we take a snapshot at a particular instant. Then we calculated the displacements, we see the displacement, the force applied. Then we take this particular atom as a reference, and we studied the movement when means we were trying to find the equation of motion for this particle. So we see that there is this force and this displacement was there, so we calculated F1 equal to this, like we have the equation for F equal to kx in the spring system. Same we calculated here force and displacement in same direction, that's why we take it positive. In this direction it was negative, and we get this result in the last lecture. This is the equation of motion for this particle inside a solid when it vibrates. So we know that when it vibrates, then the particle is gonna have a SHM, simple harmonic motion, or the vibrations. Okay. So now it is the equation. Now it's a simple second order differential equation. We need to find the solution for this. So we can find a solution just like we calculate for the Hooke's law. You know what is Hooke's law? It is nothing but when a spring is attached with the substance and it is stretched for x displacement, then the force can be given by kx. That is Hooke's law. And there we find this solution for the oscillations. That is, we can write this oscillation in any way, like x equal to a cos kx minus omega t, or x can be written in the form of sine. Means this oscillation can be represented by these equations. Also this x can also be represented as real part of a e to the power I kx minus omega t, because here e to the power I theta what gives us cos theta plus I sin theta, and real part will be cos theta. Or it can also be written, second one is as imaginary part, so e to the power I theta will be cos theta plus I sin theta, so it will give us sin theta. So they can be written like in this form also, so we don't need to write this real or imaginary. We can direct the solution as x equal to a to the power e to the power I omega t minus kx. So just like this we can solve this also, because we have the similar equation as we have for the spring system. So we can write for the displacement un as u naught exponential I omega t minus kx. It doesn't matter what is kx here or omega t here, so we can write it like this. So un will be un u naught, this solution we assumed, exponential I omega t minus, now you can see that if the distance between two particles is a, then this will be a, from here to here it will be 2a, from here to here it will be 3a, from here 4a. When it is from the infinite we are coming from, then up to n it will be na, displacement will be na. So we can take in the place of x as na. For the un displacement we can take in the place of x na. Hope you get the idea. Okay, for the un plus 1, what we can take, just in the place of x we can write n plus 1 and n minus 1, then x at the place of x we will write k n minus 1a. So we get the three equations, that is, this is first, this is second, this is third. Now we will just substitute this in this equation and find the solution actually. So let's see what the solution will come. So first of all we need to find the second order derivative for the un. So we will differentiate it twice. So we will get something like omega will came twice in the outside, so it will be look like this. m d square un by dt square will be minus m omega square u naught e to the I omega t minus k na. So here is this one point I want to mention. We see that for all the n plus 1 particle and minus 1 particle, we take this amplitude as u naught, u naught, u naught, same. So it's a very basic thing that just like you can take the example of water, means you put a rubber here inside the water, and when it oscillates, means each particle, whether it is they are transferring energy from one to another, and wave will come like this. So each particle will have the same amplitude, means not the exact moment when this particle has a maximum, it can be anywhere here, but this particle is going also gonna have this maximum value when it will be down. So it will be like this, means each particle will have the same amplitude, means maximum value will be same. So that's why it's also here, means if we take that amplitude of all this particle will be same. Okay, not at this moment but at any moment, means the maximum value will be same, that will be u naught. So we find this md square un by dt square. Now for un plus 1, we can write this equation as this un plus 1, we can write exponential I omega t minus we will multiply inside k and a and minus ka. So we will take e to the power minus ka outside, and from here minus minus plus we to the we take e to the power ka outside, I ka outside. So it is one for the plus, one for the minus. So it will come like this, like this. And from here we can see this is nothing but e to the exponential I omega t minus k na, and we are having this common in every equation. So when we substitute it inside this equation, so what we get, this part is cancelled out from each, because in the left hand side we also have this, the right hand side we also have this. So this will be cancelled out, and in the last we will left with this minus m omega square equal to beta e to the power minus I ka minus 2 plus e to the power I ka. So this will be remaining equation. From here take minus this side, it will come out this, take 2 common. Now this can be written as cos k, that's why we made this, because cos k is nothing but this equal to e to the power ix plus e to the power minus ix divided by 2. If we find another equation for sin x, that will be e to the power ix minus e to the power minus ix divided by 2. So it can be written as cos k, we take the 2 common here, then this will give us this is the solution. So this is the solution of that equation, solution of this equation, this. Now we have this solution, and this is called the dispersion relation for the phonons in 1D monoatomic lattice. This is the relation we need to find. Now we will solve this to have the multiple solutions, means now we will analyze what is the significance of this equation. Also this is for the 1D. When we calculated the same way, then for the 2D it came out to be this m omega square equal to 2 beta 2 minus cos ka cos ky cos kx cos ky. For 3D m omega square will be 2 beta kx ky kz. So this will be the solution for 3D. This is for the 2D. These are nothing but dispersion relation for phonons inside a solid. Okay, now let's see 1D equation. We take it again, this equation m omega square equal to 2 beta 1 minus cos ka. From here multiply it inside 2 beta minus, now take inside this 1 minus cos ka can be written as 2 sin square ka by 2. This came in from the equation, but where it is cos 2 theta equal to 1 minus 2 sin square theta. Okay, then this will give us this 2 sin square ka by 2. Now from here we can write omega square equal to 2 to the 4 beta by m sin square ka by 2. From here we can find the omega, that will be this, and we take the mod of sin ka by 2 because we have to take the positive value only. So omega will be this, omega will be this, and this will be some maximum frequency. So now we have the equation, the exact equation. Now let's try to take out some conclusions from this. Let's say Vs denotes the velocity of sound or the phonons, and y is longitudinal stiffness, that is y equal to beta a. Rho is nothing but mass per unit length, that is equal to mass by a. Then we know that how to define the velocity. How to define the velocity? That is Vs, velocity of sound, that is equal to rho under root y by rho. We studied in the 11th class this equation. We know how to find the speed of sound. That is where it was Young's modulus and the density. But here in the 1D, we have this longitudinal stiffness and the mass per unit length. So this will give us this y equal to beta a and rho equal to m by a. So Vs will be a root b beta by m. From here we can find the, or we can write it, take 4 inside and divide it by 4, so we'll get this equation. Now from here we know root 4 beta by m will become 2 Vs by a. Now substitute this in this equation, the root 4 beta by m. So this will give us omega equal to this. So we can rewrite this equation like this. Now omega will be omega m sine ka by 2, and omega m is nothing but root 4 beta by m sine ka by 2. Okay, so these 4 equations, both equations are same, so we'll use this equation to find the various results. So we know that k equal to 2 pi by lambda, k equal to 2 pi by lambda, and from here if we put ka by 2 equal to pi by 2, means we need to find the maximum value of omega. Then first we need to plot this curve or this curve, both will give us same. So if we want to plot them, then take omega at the y-axis, and on the x-axis we have k. Then for the value of k equal to pi by a, we will have the maximum value, pi by a minus pi by a, and for the 0 we will have the minimum value, and we will the mode, so we will get this type of curve. Don't see this line yet, just see this curve. This curve will came like this from this equation. From this equation we will get this type of curve, and maximum value at pi by a minus pi by a, and this, and minimum at the 0. So just remember this. Now we'll move forward. We have 3-4 cases here. So first case is in long wavelength region. What will be the long wavelength region? Means when our k value is tending to 0, because lambda is nothing but 2 pi by k, or k equal to 2 pi by lambda. So when lambda tends to very large, then k tends to 0. So this will be the reason for k tends to 0. So we'll study this area, that how the curve will came out in this region. So we know that when this is very small inside the sign, then we can write it directly equal to ka by 2. So let's substitute ka by 2 here. Then ka by 2, a will cancel by 2 and 2 will cancel out. Omega will be vsk. Omega will be vsk. This is the same relation I told you before when I gave you some questions, that this was a dispersion relation for phonon in the long wavelength region. Just remember this point. So you know that this is the equation of a line. So for the very small value of k, means k tending to 0, long wavelength region, we will have a straight line equation. So you can see here, this is the region, and this curve is mostly a straight line in this region when k is very small. This is a straight line. Then after that it will start to divert. So case 1 was in the long wavelength region. So dispersion relation of phonon in long wavelength region is this, omega equal to vsk. Just remember this. Now the phase velocity and the group velocity. First you need to know what are these phase velocity and group velocity. You know that when there is this wave moving, then the velocity of single monochromatic wave is called phase velocity, and there are multiple waves which just overlap each other and form an envelope, then that whole group of waves when moves, that velocity of that group will call group velocity. And we know the formula for the phase velocity, it is omega by k, and for group velocity it is d omega by dk. So we can write from here Vp equal to omega by k, so that will give us Vs, and for group velocity we know that d omega by dk, so just differentiated with respect to k we will get Vs. So we get that Vp equal to Vg, means both are velocity same, and when these both velocity came to be equal, then we are talking about a medium which is not dispersive. So we will call that, for this reason, for long wavelength reason, we will have a non-dispersive medium. When k is tending to 0, then we will have a non-dispersive medium. So what are dispersive and non-dispersive mediums? These are nothing but just like we see a prism. We know that when a single light of visible light came, and in the prism it divided. So we know that for red color the wavelength is very large, that's why its refractive index is very less, and speed of light is greater for r and lower for v, because speed is related with c by mu. The more the refractive index, less the velocity. So refractive index for mu is, for red, is very less, that's why we have large value of v inside this for red, and for low for violet, because lambda for violet is less and refractive index will be larger for v, and when it will be larger v will be small. So we find that these all are traveling with different velocities, so that's why this medium called dispersive medium. And when they all travel with the same speed, we call it the non-dispersive medium. So a medium in which Vp depends on its wavelength, means what will the phase velocity, that will depend on phase, or the lambda, means as red is having the more lambda, it is having the more velocity, and it is less lambda, less velocity. So when it the speed depends on the lambda, we call the medium as dispersive medium, and when they both are equal, then we call them non-dispersive medium, means group and single wave move with the same velocity. So if you get the idea, so in the long wavelength region we are having a non-dispersive medium, Vp equal to Vg. So from here you can find the definition of Vp and Vg. Velocity of a monochromatic wave, that is a single wavelength, called the phase velocity, and group velocity, wave packet, that is, we will study about it in the quantum mechanics more. So here just you get the idea. Envelope of a group of waves with slightly different wavelength interfering with one another in a way that the amplitude of the envelope is non-zero only in the neighborhood of the particle. So this is some kind of wave packet. These are the single waves. Now case second, in the short wavelength region, when wavelength is short, then 2 pi by lambda, then k will be large, we will get k as large. So we know this expression, we find for the 1D monoatomic lattice, 2 Vs by a sine Ka by 2. When k is large, just write the expression for Vp and Vg. Omega by k will give us this. Omega will be this, and this is like this. And for Vg, d omega by dk, just differentiate it with respect to k, we will get this expression, Vs cos Ka by 2. Now from here you can see that this Vp and Vg are not equal, both are different. So that's why we call this medium, for the short wavelength region, the dispersive medium, because both velocities are different, they depending on the lambda, because k depend on lambda and Vg Vp depends on k. So that's why we call it dispersive medium. Now let's take the third case, that is the cutoff frequency, means inside a solid the atoms gonna have maximum frequency, means they can't have the frequency more than that value. And what will be that? So omega equal to this expression we know. So just the maximum value can be, just put this 1, then it will be maximum, that will be 2s Vs by a. So when we put this 1, then Ka by 2 should be pi by 2, K by 2 should be pi by 2, and we will get for k equal to pi by a from there, and k equal to 2 pi by lambda, and lambda will be 2a. So this will be the maximum wavelength of the wave which can travel inside a solid, or can generate it inside a 1D monatomic lattice. This will be the lambda. So what's the significance that so maximum omega will be 2 Vs by a, that is the cutoff frequency. So if lambda is greater than this, means if lambda equal to 2a, just put it here, or k equal to pi by a, substitute it here, k equal to pi by a, then we will have pi by a to a cancel, this will be 1. So we have maximum value for Vp, and when we put it here, pi by a to a cancel, pi by 2, this will give us 0. So group velocity will be turn out to be 0 at the k equal to pi by a. So when we increase frequency more lambda more than this, then things wanna go differ, and the waves would not be able to travel or generated inside a solid. That's why this is called the maximum frequency or the cutoff frequency. Okay, so thank you. Tomorrow we'll discuss some questions, then we will go to the diatomic lattice vibrations. Okay, thank you.